Today's video is short, but it is fundamental. One of the most important things we're going to do all year. We're going to do it over and over and over again. So let's say there's a function, f of x. I don't know what it is, but I do know that its derivative, f prime of x, is 6x squared. How can I figure out what f of x is? Well, first of all, f of x has a name in this case. F of x is an antiderivative. So we say f of x is an antiderivative of f prime of x. You might be able to tell just by looking, but let's figure this out. So if f of x, I'll say f prime of x is 6x squared. Well, that's a power. So it must be the derivative of another power, and you must have gotten that derivative from f of x using the power rule, which means that f of x must have had an exponent that was 1 higher than 2, because that's how its derivative would have ended up being x squared. So the antiderivative of a power is 1 higher than the power itself. And then for the coefficients, now, if you were to take the derivative of f of x, you were to bring down that 3. But that's not a 3, that's a 6. So I didn't just bring down a 3. Or at least, when I brought down the 3, there must have been something else there to multiply it by also. So the question is, what must have been here such that when I multiplied it by 3, I got a 6? What must have been in that spot so that when I multiplied by 3, I got a 6? Well, if we go take a little trip back to 3rd grade, you'll remember that that whole sentence I just said is another way of saying, what is 6 divided by 3? What number do you have to multiply by 3 to get to 6? That's the same thing as saying 6 times 3. Sorry, 6 divided by 3. So to find the antiderivative of 6x squared, I took the exponent and I raised it, lifted it up 1. And then at the same time, I also divided the coefficient by my new exponent. That's it. Raise the exponent by 1, or lift the exponent up by 1. Maybe increase is a better word there. Increase the exponent by 1, and then divide by the coefficient by the new exponent. That's it. That's a rule for finding antiderivatives. So now we've got 2 different things we can do with a power. We can take its derivative, we know, to bring down the coefficient and then lower the exponent by 1. But we can also now take the antiderivative of any power by raising the exponent by 1, increasing the exponent by 1, and then dividing by the new exponent. That's it. We can write this a little bit more formally. For any function, for a power, the antiderivative, and this is a fun little trick here, when we have f of x, if that one is the derivative of something, well, but there's no prime there, like what can I call its antiderivative? So the trick here is we use capital F to show the antiderivative of lowercase f. The capital F, so the antiderivative of f of x, is x to the new exponent divided by the new exponent. And that's it. By the way, if there is a coefficient in front, then it's just still there anyway. We know that from our properties of exponents. So here are a few examples we can use. We're going to find the antiderivative of each one of these. Notice how this one is in prime notation already, so its antiderivative would be regular old f of x. Would be take x to the new exponent, increase the x squared by 1, but then divide the 6 by the new exponent. The same one we had a minute ago. And then for the next one, the next term, 18x to the new exponent, we're going to increase it by 1, and then divide by the new exponent. And then plus 3. Remember, this is x to the 0. Anytime there's no x at all, it means there are no x's, so it's x to the 0. So we're going to raise that, increase that exponent by 1, and then divide by the new exponent. Now, it is silly to leave your answer like this, although if you did, you wouldn't lose credit. But it makes a lot more sense to do the division here. 6 divided by 3, 18 divided by 2, and of course we're not going to actually put the over 1 there. 3 divided by 1 is just 3. If you can do this in your head, you don't need to write it out that way. The goal is for you to start being able to do this in your head pretty quickly with exponents and power rules. One note here, though. Notice how I did not say find the antiderivative of each. I said find an antiderivative of each, which implies there are others also. And there are. In fact, there's an infinite number of antiderivatives of every power. The reason for that is because let's say f of x was 2x cubed minus 9x squared plus 3x. We know f prime of x would in fact be 6x squared minus 18x plus 3. But if f of x were 2x cubed plus minus 9x squared plus 3x plus 2, it would have the same derivative of 6x squared minus 18x plus 3 because the derivative of that last term is just 0, so it wouldn't change what f prime was. Or that could have been a 20, or a 201.3, or a 201,352 divided by pi. It doesn't matter what that number is. It can be anything, and the derivative of f of x would still be f prime of x is 6x squared minus 18x plus 3. So in order to show that, what we do is we use a letter at the end, a constant. You don't have to call it k, but everybody does, so you'll just, everybody calls it k. What am I talking about? Everybody calls it a c. So you'll sound a little bit weird if you don't, but you can call it whatever you want. 2x cubed minus 9x squared plus 3x plus c means that there could be some other constant at the end. We don't know what it is. The fancy name for that is called the constant of integration. We'll see why later on. But for now, all you have to know is include that plus c at the end. And this power rule works for exponents or powers that don't look like polynomials, like h prime of x is 3 over x to the 5th. Well, that's the same thing as 3x to the negative 5th. Minus 2x, that looks fine, and 2 times the 4th root of x cubed is the same thing as 2 times x to the 3/4. So if we rewrite our radicals and our rationals as exponents, we can start using the power rule. So if that's our new way of writing h prime of x, h of x would be 3 times x to the negative 4th, because we're increasing by 1, but when you take negative 5 and increase it by 1, you get negative 4, dividing by that new negative 4, minus 2x squared divided by the new exponent, plus 2x. This gets a little bit messy here, but take 3/4, increase it by 1, you get 7/4, because 3/4 plus 4/4 is 7/4, and then divide by 7/4. Of course, we're going to clean this up. Negative 3 over 4x to the 4th minus x squared. And then for the 2 over x to the 7/4, 2 over 7/4 is the same thing as 2 times 4/7, which is a much more reasonable way to write it. So I'm going to write plus 8x to the 7/4 over 7. And so that is the antiderivative h of x plus c.